Thank you so much, Professor Consta, and thank you, Professor Shah. So my name is Marina. I'm a PhD candidate at Purdue University, and my presentation is titled Nanomodification on Cement Pastes, Microstructure and Pore Structure, the Acceleration of Natural CO2 Capture of Hardened Cementitious Composites. So this will be the overview of my presentation. I will start with the introduction, then I will go over the materials and methods, and I will discuss the results, and I will go through some final conclusions. So in terms of the introduction, CO2 emissions have been rising every year, and we're getting to alarming levels, right? We do know that cement production, cement manufacturing is one of the main contributors to this. We can estimate that 8% of all CO2 emissions globally are due to the production of this material. So what can we do about it? A good approach that's been going on for quite a few time now, it's carbonation. It's the enhancing this natural CO2 sequestration that we experience in cement-based materials. What happens with this reaction is that CO2 will penetrate through the pore structure, and it will react with the cement hydration products that are in the solid phase of our matrix. Mainly, it's calcium hydroxide reacting and forming calcium carbonate in water. So if we can enhance this reaction, whether that's accelerating the reaction or enhancing the amount of CO2 that it's uptaking, we can lower our environmental impact when we have this material. So one of the approaches that it's usually taken is CO2 curing, which has been found that it increases CO2 uptake, and it also provides better mechanical properties in some cases. Also, the addition of titanium dioxide nanoparticles have been found to enhance these mechanical properties, provide photocatalytic properties as well, and increase durability. And in one of our recent studies, we actually found out that it also increases CO2 uptake of our cementitious composites. However, the effect of titanium dioxide nanoparticles and the CO2 concentration in the air on how fast this reaction is not known. Therefore, the objective of this particular study is to understand the mechanisms that govern these changes in the CO2 uptake rate, or the acceleration of this phenomenon produced by the nanomodification of cement pastes and those CO2 concentrations. So for the materials and methods we use ordinary Portland cement, water, of course, because we're doing cement pastes, and 2% of titanium dioxide nanoparticles, 0%, so no nanoparticles, and 1%. We casted a total of 30 prisms, half of them with no titanium dioxide nanoparticles and half of them with those nanoparticles. As for the curing procedure, these samples stayed in the mold for 24 hours, then in water curing until the 28th day, and then we exposed them to a pre-curing treatment so that we could lower the internal moisture to prepare them for that CO2 exposure. So to assess that effect of the titanium dioxide nanoparticles on this CO2 uptake rate, we exposed the samples after those 28 days and after that treatment to an accelerated CO2 exposure for 8 hours. So in terms of the CO2 uptake quantification, there are a few methods to do so. One of them is the thermogravimetric analysis, or TGA, which we will basically measure the weight of the sample that you're testing while you're increasing that temperature. Therefore, if you know the temperatures or the range of temperatures where your compounds will be composed, you can calculate how much of that compound you have in your sample. So in terms of the calcium carbonate, which is the compound that is resultant from the carbonation, you can quantify how much that is, and therefore comparing that to the sample that's not been exposed to that CO2, you can estimate how much CO2 has been uptaken in that reaction. Another method is the weight method, which basically accounts for the increasing weight due to the change from calcium hydroxide, in this case, to calcium carbonate. It has a bigger mass, and therefore you're increasing the weight of the sample. The only, I guess, issue with this method is that because the reaction also produces water, you have to account for that water, and it's sometimes a little bit difficult to estimate. So what we decided to do is we come up with our new method that will not only let us how to estimate that CO2 uptake, but also how to estimate the CO2 uptake rate, or how fast that reaction is happening. This method, we call it the CO2 sensor monitoring, where we took our CO2 sensor, which will measure over time that CO2 concentration in an enclosed environment, and therefore we can estimate how much CO2 was uptaken in our material. The CO2 exposure test that we tested our samples with consisted of, first, we placed our samples inside of an enclosed or sealed chamber along with the CO2 sensor. Then we let CO2 enter that enclosed environment, making sure all of the air was being taken out. And then when we reached the desired concentration, we closed both valves and the exposure started. We studied 3 initial CO2 concentrations, which were 25% CO2, 50% CO2, and 100% CO2. And once that was reached, we exposed the samples to 8 consecutive 1-hour cycles. So that means that each hour we would be adding more CO2 until we reached to that desired concentration every time. So for the results of this test, these are the results for the CO2 sensor monitoring. As you can see, we have the CO2 concentration on the y-axis and the time on the x-axis. Each color represents the different initial concentrations that we have. And the 2 lines represent the samples that were nanomodified and the samples that were not nanomodified. And on this graph, you can see the CO2 consumed per gram of cement, so this per cycle. So this relates to the CO2 uptake rate, or how fast we're doing that reaction. And as you can see from these results, both increasing CO2 concentration and nanomodifying the sample did enable for more CO2 capture, as well as capture at a faster rate. However, the contribution of these titanium dioxide nanoparticles in the CO2 uptake rate was higher when we expose it to lower CO2 concentrations. As you can see here, this difference between the green and the red lines, which where the lower concentrations is higher than this one right here. And we think, or this might be due to the nanomodification of the samples, enhancing carbonation at the beginning of the cycles, due to the reduction of porosity, preventing it from further happening. So we also wanted to verify the CO2 uptake with the other 2 methods that we commented earlier. So in terms of the weight method, we do see pretty similar results for all of them, except for one of the samples that were not nanomodified at 100% CO2 concentration, which might be due to that underestimation due to not being able to account for all of the water loss during that process, which is a difficult thing to do. But we did see that in all cases, titanium dioxide nanoparticles did increase CO2 uptake. In terms of the TEA, we decided to test to see if we're indeed creating calcium carbonates, and we compared this with the samples that were exposed to 25% CO2. And what we saw is that nanomodification, the samples, actually, we increased the CO2 uptake by 32.7%. So the trend here is clear. When we add titanium dioxide nanoparticles, we're increasing the CO2 uptake, and that is consistent with all methods that we're seeing. So why is this happening? We do know that porosity is reduced when we add titanium dioxide nanoparticles. So this should result in a reduction of the CO2 uptake because we're reducing the diffusion of CO2 into the pore structure. However, we're getting the opposite results, right? We're having counterintuitive results. In one of our previous studies, we saw that this may be due to the reduction of the crystal size of the CH. However, is there any other mechanism that's taking a part of what is contributing to this? So for this, we tested our samples with a 3D X-ray microscope scan. We tested the samples that were not nanomodified and the samples that were nanomodified. And what we saw is that, yes, porosity is reduced a little bit when we add titanium dioxide nanoparticles, but the pore surface area of those pores, of the pore structure, is increased. So this may cause this acceleration of the process of the carbonation because we have higher pore surface area, so the CO2 has more surface ability to react with. And this is seen in this figure that I'm showing you to exemplify this. On the top, we have a pore of a reference sample, and on the bottom of a nanomodified sample. Even though we may have the same overall porosity, because we're refining that pore structure, we have more surface, so the CO2 can react with more CH around that surface. And with all of this data, we decided to come up with a CO2 uptake rate estimation model. We don't know from the literature that carbonation depth is usually proportional to the square root of time. So what we came up with is with this equation that the CO2 uptake in grams is equal to the carbonation rate coefficient, which is something that we came up with, and the square root, times the square root of time. And this carbonation rate coefficient is affected by both the nanomodification and the CO2 concentration that we have. So with this data, we estimated the carbonation rate coefficient for each of the conditions using the least square method. And these conditions were the two percentages of titanium dioxide nanoparticles and the three initial CO2 concentrations. These are the estimations that we got, and as you can see, if you see on the y-axis, the estimated CO2 uptake with this formula that I'm showing right here, and on the x-axis, the actual measured CO2 uptake, we're getting a pretty good estimation. And also, as you can see, adding those nanoparticles has a much bigger effect on the samples that were exposed to lower CO2 concentration. And that might be due to CO2, 100% CO2, so having high levels of CO2 in the air is already accelerating this reaction a lot. So the effect of titanium dioxide nanoparticles is not as significant. Whereas if you lower the CO2 concentration, this effect is enhanced. As you can see, we're getting almost 40% of increase in the CO2 uptake rate. So we're accelerating this reaction around 40%. In the conclusions or the main takeaways of this study, we saw that the CO2 uptake rate is enhanced when we're adding titanium dioxide nanoparticles for all CO2 concentrations. However, this effect is more significant when we have lower CO2 concentrations. And we saw that this may be due to then the refinement of the pore structure, where we do have lower porosity, but our pore surface area is increased. Also, I wanted to add that if you want more information about this, you can check out our paper, scanning that QR code. I'll leave it for a minute.